When people first see images of two different colors of water flowing side by side in the ocean, the reaction is almost always disbelief. It looks unnatural, even staged, as if someone has drawn a line across the sea. Waves roll in the same direction. The wind blows evenly across the surface, yet the waters do not immediately blend. For centuries, sailors noticed this phenomenon without understanding it. And in the modern age, viral videos have turned it into one of the most misunderstood natural events on Earth. Many people describe it as a place where oceans refuse to mix, or where invisible walls divide the sea. The truth, however, is far more fascinating, more complex, and far more grounded in real science than the myth suggests. The most famous example of this phenomenon occurs near Cape Horn, where the Atlantic Ocean meets the Pacific Ocean. It is also observed in places like the Gulf of Alaska, where glacial meltwater flows into the ocean, and near the Strait of Gibraltar, where the Atlantic meets the Mediterranean Sea. In each case, the waters appear to sit side by side, maintaining distinct colors and textures for long distances. Despite appearances, these waters are not permanently separated. They do mix eventually, but the process is slow, layered, and governed by physical properties that are invisible to the naked eye. The key concept behind this phenomenon is density. Ocean water is not uniform. Its density changes based on salinity, temperature, and the amount of dissolved material it contains. Salinity refers to how much salt is dissolved in the water, while temperature affects how tightly water molecules are packed together. Colder water is generally denser than warmer water, and saltier water is denser than fresher water. When two bodies of water with different densities meet, they do not instantly blend as two liquids poured into a glass. Instead, they form what scientists call a density gradient. This gradient creates a boundary layer known as a halocline when salinity is the dominant factor, or a thermocline when temperature plays the larger role. At these boundaries, mixing still happens, but it happens slowly, through turbulence, wave action, and molecular diffusion. From the surface, this boundary can look sharp and dramatic. Even though on a microscopic level, the waters are constantly interacting. At Cape Horn, the Atlantic and Pacific Oceans differ in both salinity and temperature. The Atlantic is generally saltier due to higher evaporation rates, while the Pacific receives more freshwater input from rainfall and rivers. The winds in this region are among the strongest on Earth, and the currents are powerful, yet the density differences remain strong enough to maintain visible separation over large areas. The waters are constantly mixing below the surface, but the process can take days, weeks, or even longer to fully equalize. In the Gulf of Alaska, the effect is even more visually striking. Here, massive volumes of fresh water from melting glaciers and rivers flow into the ocean. This fresh water carries sediment, giving it a lighter, milky appearance compared to the darker blue ocean water. Because fresh water is less dense than salt water, it floats on top rather than sinking and mixing immediately. The result is a clear boundary where the river and glacial runoff meet the sea. Over time, waves, tides, and currents gradually mix the waters, but near the surface, the contrast remains visible. The Strait of Gibraltar offers another compelling example. The Mediterranean Sea is warmer and much saltier than the Atlantic Ocean. As Atlantic water flows into the Mediterranean at the surface, Mediterranean water flows out beneath it, creating a two-layer exchange system. The waters do mix, but the density difference maintains separation across depth layers. This exchange has been measured, mapped, and studied in detail by oceanographers, confirming that the boundary is not a wall, but a dynamic interface shaped by physics. It is important to understand that the idea of oceans not mixing is misleading. All oceans are connected. Over time, all ocean water circulates around the globe through a system known as thermoline circulation. This global conveyor belt moves water across vast distances, driven by differences in temperature and salinity. The process operates on timescales of hundreds to thousands of years, redistributing heat, nutrients, and dissolved gases. What we see at the surface are temporary boundaries within a constantly moving system. Human perception plays a role in why this phenomenon seems so dramatic. Our eyes are highly sensitive to color differences but blind to density gradients. We cannot see temperature differences or salinity levels directly. When sediment, algae, or organic material enhances the color contrast, the boundary becomes visually striking, reinforcing the illusion of separation. Underneath the surface, however, turbulence is constantly breaking down these boundaries. Scientists have studied these interfaces using instruments that measure conductivity, temperature, and depth. These measurements show smooth gradients rather than sharp walls. Satellites also detect differences in surface temperature and color, allowing researchers to map these boundaries across entire oceans. These tools confirm that what appears to be a line is actually a zone of gradual transition. Historically, sailors observed these boundaries long before modern science could explain them. Early explorers described changes in water color, taste, and behavior. Some believed they marked the edge of the world or zones of danger. These interpretations were shaped by limited knowledge and the harsh conditions often present in these regions. Today, we understand that these areas are not dangerous because of mixing failure, but because of strong winds, powerful currents, and unpredictable weather. These boundaries also play an important role in marine ecosystems. Differences in temperature and salinity affect nutrient distribution, which in turn influences where plankton grow. Plankton form the base of the marine food web, supporting fish, birds, and larger predators. Many species rely on these boundary zones as feeding grounds because nutrients tend to accumulate there. In this way, the same physical processes that create visual separation also support life. Climate change is affecting these systems in measurable ways. Rising temperatures increase glacial melt and alter rainfall patterns, changing the balance between freshwater and saltwater. This can strengthen or weaken density gradients, affecting circulation and nutrient flow. Scientists monitor these changes closely because disruptions to ocean mixing can influence climate, fisheries, and global weather patterns. One of the most persistent myths surrounding this phenomenon is that religious texts or ancient beliefs predicted oceans that never mix. While some ancient writings poetically describe boundaries in nature, modern science does not support the idea of permanently separated seas. Such interpretations arise from symbolic language rather than physical observation. Scientific understanding relies on measurement, repeatable observation, and physical laws, all of which show continuous interaction between ocean waters. The fascination with this phenomena reflects a deeper human tendency to interpret natural patterns as mysteries. When something looks unusual, we instinctively search for hidden forces or dramatic explanations. In reality, the explanation is rooted in basic physics that also govern everyday experiences, like why oil floats on water or why hot air rises. The ocean is simply applying these same principles on a massive scale. Understanding how and why oceans mix slowly helps scientists predict climate behavior. Ocean circulation regulates Earth's temperature by transporting heat from the equator toward the poles. If mixing patterns change, climate patterns can shift. This is why oceanography is not just about the sea, but about the planet as a whole. The place where two oceans appear not to mix is not a violation of natural law. It is a visible demonstration of it. What we are seeing is density in action, shaped by temperature, salinity, and motion. It reminds us that nature often operates in ways that are subtle, layered, and gradual, rather than abrupt and absolute. Over time, the waters do mix. The boundary dissolves, reforms, and shifts with changing conditions. There's no permanent line, no invisible barrier, and no defiance of physics. Instead, there is a constantly evolving system, balancing forces that have shaped Earth's oceans for millions of years. By understanding this phenomenon accurately, we replace mystery with knowledge and spectacle with science. The oceans are not divided by walls, but connected by motion. What appears separate at the surface is united below. moving as part of a single global system that sustains life and regulates the planet. In the end, the real wonder is not that the oceans appear not to mix, but that they mix it all. Across such vast distances, depths, and timescales, the boundary we see is only a moment in a much larger story, one written by physics, shaped by Earth, and still unfolding today.